Hello everyone, this is Rui PCB, your trusted PCB partner. Today we continue to discuss the art of double-sided PCB layout, laying the foundation for success. In the previous episode, we introduced the first two layout strategies. Today we will continue with the remaining layout strategies. So, layout strategy 3, isolating signal flow from high noise areas. This is key to ensuring circuit performance, especially for analog and mixed signal circuits. When arranging linear signal flow, you should lay out the functional modules in a linear fashion according to the signal processing sequence, from left to right or from top to bottom as much as possible. For example, signal input, preamplification, ADC sampling, MCU processing, DAC backend driving, interface output, and so on. Take my current circuit as an example. This interface here is an RF signal input. After receiving the signal, it is split into three paths. One of these paths processes a specific frequency, passing through a filter, then an ADC, then an amplifier, and finally converts it into a digital signal, which is then input to the MCU. The other two paths work the same way. Each goes through its own filter, then an ADC, then a voltage comparator, and finally is input to the MCU. This effectively isolates the digital and analog signals, and the flow of digital signals follows the direction of the analog signals. It's unidirectional, flowing sequentially from top to bottom, and ultimately delivered to the MCU. This is to prevent signal backflow. A linear layout can effectively stop signals from coupling through space and feeding back into the weak input signals, which could otherwise cause interference or unwanted stimulation. So, for example, if we lay out the signal path, let's take this path as an example. It goes downward and then continues along this direction. If I place the two output signals near this area, the signals they generate could affect the input signal, so we need to avoid this situation. For analog signals, it's especially important to control the flow direction and prevent any backflow. Now, the concept of isolation strips. Between noise sources and sensitive components, we can use their physical locations to create natural isolation. If there is enough space on the board, you can even leave some distance between them, or place some critical or non-critical low-speed digital signals in between. In this circuit, I've implemented isolation between digital ground and analog ground. As you can see, at this position, this R39 is a magnetic resistor. Looking at its network, on this side it's connected to GND, and on the other side to AGND. Then, through the negative feedback network, you can also see that the negative feedback is connected to GND, which mainly manages the digital circuitry in the lower section. Then, looking at the negative feedback network, it's connected to AGND. For all analog signals, AGND is used for negative feedback to prevent interference between digital and analog signals. Alright, layout strategy 4, the Hart layout method for power and ground. Power is the lifeblood of a circuit, and the quality of its layout determines the overall health of the entire circuit. The power input is centrally managed. The power entry fuse, common mode inductor, PYE protection devices, and the first stage of large capacity filter capacitors are all placed together at the board's entry point, forming a compact power zone. This is shown here. USB is used as the power supply, and on the left side we can see it more clearly in the 3D view. As a primary power source, the USB's entry point is conveniently located in this specific area. It efficiently supplies electrical power through the USB connection and simultaneously charges the internal battery unit. Here I also have a spot for the battery, and near the battery there are some battery management chips. And in here, the larger capacitors are where some big capacitors are placed. Alright, the voltage regulator at the heart of the board, the main regulator, usually an LDO or DC-DC converter, is placed at the physical center of the board or close to the main power consuming components such as the MCU. So this area here is the main power supply section that provides 3.3V, and it's located relatively close to the MCU. The upper part of the power supply is also like this, so it won't be placed too far down, but rather in a relatively central position. Next, the proximity of the decoupling capacitors. This is one of the most important and strictly enforced rules in layout design. The decoupling capacitors for each IC must be placed as close as possible, with no gaps to the IC's power and ground pins. This is quite obvious. Take the MCU as an example. In the middle, these are its capacitors. These are its decoupling capacitors, and these are its power pins. The decoupling capacitors must be placed extremely close to the power pins. Similarly, other chips also have corresponding decoupling capacitors and power pins, and these must be properly placed. All right, next is multi-stage filtering. From the entry point, the power supply goes through multiple stages of filtering and voltage regulation, so that by the time it reaches the chip, it is as clean as possible. Handling it at the centralized entry point can prevent external interference from causing crosstalk on the board. That's why, as you can see, a large capacitor is placed at the USB entry point, and similarly, a large capacitor is also placed near the battery. Small capacitors are also used, all to achieve multi-stage filtering and prevent external interference. All right, that successfully concludes this comprehensive introduction to effective double-sided PCB layout strategies. If you genuinely enjoyed this informative video and found it helpful, please consider subscribing to my channel for even more valuable content and future updates. Thank you all very much for watching.